All right, I don't really have a purpose on this video, but I do have the RevC finally going. I had an issue with ISOSpy, yeah, right? And it turns out that I had just populated the wrong part. There was supposed to be a 768 ohm resistor, and I hand populated the whole board. And I actually populated with a 20 ohm resistor, so it should have been 768 and it was 20, and it was just totally hosing the ISOSpy bus. So it is just as robust as the previous version now. I verified it here with my with my Gold Master Rev B board. So this is the Rev C board, and I've been playing around with the grid charging. I intentionally put like a severely unbalanced pack in to see how quickly we can balance it. And if your cells are severely unbalanced, like some cells are at 20% state of charge and others are at like 80% state of charge, it could take like up to 24 hours for this to balance it. So when you're assembling the packs, if you have a method of discharging the pack, I highly recommend you do it before you put it in the car, because from my testing today, through the middle 20 to 80% of the state of charge, you can do 10 millivolts of offset per hour. And so I had it balanced, and I took a starting value, and then I waited 6 hours and took the finishing value, and basically 10 millivolts per hour. So this pack was initially 250 millivolts off because one of the 18S modules I charged to 3.8 and the other one was at 3.5. So that took, it would have taken over a day. And so what I did is I just took the cells out and I manually discharged them using, I have a programmable load that I can discharge them with. And right now I'm charging them back up. So Natalia, one of our beta testers, has had some feedback that the grid charger that comes with LiBCM is quite slow, and it is quite slow. It charges at, what is the value here? Hold on, done some math. It charges at 62 watts. So this is an 888, is that right? No, it's a 942 watt hour pack. So if this were totally empty, it would take about, I don't know, 14 hours to charge. That's basically overnight, and I don't anticipate that it will normally be totally empty when you're grid charging it. But nonetheless, if you do want to grid charge faster, LiBCM supports LED grid chargers, and this is a larger one I was going to use, except that it's very expensive. This grid charger here is $115. I haven't priced it in a while. It might be a cheaper one. I've bought a whole slew of them. Regardless, this was an expensive grid charger. This is a 1400 milliamp charger. It's totally compatible with LiBCM, so you can plug these wires in exactly as you plug the ones in here. It has the same exact pin out. You do need the B version. So if you're going to use this supply, it's the HLG 320H C1400B. The B is important. There are other, there's plenty of it. This is a pretty standard format. You need to be able to control the pulse width modulation to control the current output on this type of supply. Otherwise, you can't balance the cells. So yeah, this is what it comes with. This is a 350 milliamp charger, and again, that's about 14 hours to charge a completely empty pack. And the 1400 here is, what is that, 9? It's about 3.5 times faster. So this would take your charge time down to about 4 hours from a completely empty pack. And then if you're in a real hurry, I'm using it right now. This is a TDK Lambda Gen. The Gen Assist series is an amazing single quadrant power supply. And you can see right now I'm pushing 187 volts at what was 11.5 amps. It has just started to turn down because I have the programmable voltage cutoff on it. So we're getting to the 3.9 volt, which is the finishing value. We charge to 3.9 volts. But this is the, you want to charge in a minute. This will charge the pack from empty in about 25 minutes. And they make these larger. This is a 3.3 kilowatt model. They make them up to 5 in this 2U rack mount, and then you can get them up to whatever the hell you want. You can get them up to like 10U, and they're like 50 kilowatts or something. So I'm gonna go ahead and turn this off now. So LiBCM, I have programmed it to where it can control these TDK lambdas, that is a very future option, so it's not there initially. But anyway, you can buy these. I've talked about these before. You can buy these broken on eBay for next to nothing. I paid like $60 for this or something, maybe $70 for this unit. They're like thousands of dollars new. I've never found one I can't fix, and I know I've talked about them before, but I love the TDK Lambdas. I've got two up here. These are some smaller ones. This is a 30 volt, 25 amp, 150 volt, 5 amp. This one is a 300 volt, 11 amp. They make a 200 volt version, which would be perfect for LiBCM. It's like 200 and it's, I think it's like 17 amps or something, 16 and a half amps. I've got some more TDKs hiding around there. There's two over in the corner. I really like these power supplies. They're really awesome, and again, you can get them super cheap. So kind of a tangent there. I don't really, again, have a purpose on this video. Other than that, I still haven't put this in the car because I was fighting that, that incorrect resistor I mentioned at the beginning here. But here is LiBCM running and grid charging, and you can see that now that I've turned the supply off and we're not cranking 11 amps into it, the cell voltage has dropped down. So I'm going to drop this down to maybe, I don't know, 5 amps. Do a little topping charge here. Eventually this will be all automated as well. Basically the way I have the blue and gray wires here, this is just a pulse width modulation train. So anything that can take a pulse width modulation control, which the Lambda Gen can, you can control it externally. And then you can also power devices. This cable has an IGBT and IGBT on it that can basically turn power supplies on and off. And this can turn on and off power supplies up to, I think the fuse in here is 4 amps. So you can't pull more than 4 amps, which at 120 volts, you wouldn't be able to charge more than like 200 to 300 watts. So you can see here that we just turned the fans off. So LiBCM is a little confused because it's not expecting this external controller. It's trying to see, if you see the controller is off now, that's what this LED means, is we've turned the controller off. This LED means that the controller is on. So anywho, you can see right now that I've got a 30 millivolt delta between the most and least charged cell. So this would take 3 hours to balance with LiBCM, and at this point that's fine. 3 hours is not a problem. It was the 25 hours that was going to be problematic for my testing here tonight. Anyway, I've got some of the beeper stuff plugged in now if the cell voltages get too charged, which on this beta code, the cell voltages can still get charged. I think Natalia has made some changes on there and has a pull request pending, and I just haven't looked at it. I've been both busy and tired, so kind of taking a little break, but I'm still working on it. I'm just, yeah, anyway. That is probably all I have to say right now. I'm going to finally go throw this in the car. Again, that ISO SPI issue is really annoying to find. Didn't learn anything new, but just, I'm going to be excited to have a pick and place machine. So on the note of the pick and place machine, just because I have it sitting right here, I've purchased several screens and none of them worked. There is kind of a common pinout here, but it didn't ultimately matter. I begged and pleaded with the manufacturer here, and I finally convinced them to send me a new screen. And their minimum order was $250, and the screen was like $30. So I got a bunch of tips or whatever. Whatever. I really don't want to redesign this machine. I've been looking at the OpenPNP, and OpenPNP is great. I just don't want to take the time to learn it. So I'm hoping I can get this machine to keep going, and then maybe a little bit down the road I can add the camera vision. That is something really exciting about OpenPNP, is of course having the camera vision, because it can much more accurately replace the parts. This thing always gets the parts on the pads, but sometimes they're really off-centered. Typically the solder wetting will pull them into place when the solder reflows, but it's not always the case. So anywho, I will have a screen coming. But the screen's not going to be here for a little bit. It is shipping from China, and I imagine it will take a week or two, maybe even more, to get here. That's going to be with the fast shipping. So anyway, what I'm going to do in the meantime is I'm just going to sit down, watch some TV, and make a bunch of cables. So, for the ultimate LiBCM release, it's not really going to delay it a whole lot, waiting for that screen, because I'm just going to sit there and make cables. The cables take longer to make than the PCB does. So I can make these PCBs pretty quickly because, again, the pick and place machine does it all, and then I'm just kind of soldering on some final components. But yeah, making the cables is a chore. You've got, right now there's 12 cables to connect the 3 different 18S configurations where you have 2 18S plus, 2 18S minus, and then 1 18S plus and 1 18S minus. We've been talking a little bit about consolidating that. I do want to, I'll have a follow-up video where I'm kind of showing what it entails, what I've been proposing. But anyway, I've got right now, the 12 cables. There's 5 cables per vehicle, per configuration, module configuration. So it doesn't ultimately matter if there's 12 different types of cables or 5 different types of cables. At the end of the day, if you sell 100 units, there's going to be 500 cables that I have to make. So each cable has 5 high current, each LiBCM has 5 high current cables. And it has these 2 cables here. I've got to prep all of these power supplies, which I've done about 25 on. And then the BMS connectors, whichever way we end up going with them, those take a long time to make. Crimping all of the heads onto these, this is the 18S one, it's got 20 connectors, and I have to hand crimp this. The 2 on the end are larger connectors, so I have to crimp ferrules onto them first. And it's I wouldn't say it's error prone. I have a cable tester on these that tests if they're good or bad, which I need to work on that some more. But putting these in, I've talked about it before. Sometimes these get they don't go in the slot correctly, and you can't remove them without cutting the jacket on the side. So even if it's like a 0.1% rate, which is probably higher than that, you multiply 99.9, so 99.9 pass. Oh, come on, go to the bottom. 0.999, and you raise that to the power of 20, and yeah, okay, so yeah, it's definitely higher than that. Let's say like it's a, I don't know, 3%. So did I do that right? Yeah, 99.7. So you can see that the chances go down. So I could actually probably come here and actually figure out what my failure rate is depending on me. So it's higher than 98%, that's for sure. Let's go with 99%. So if you get 99% in, you only have a 4 out of 5 pass rate. So that's an annoyance here. On the beta units, when they didn't go in properly, I literally just cut this tang out and then removed them, replaced them. But I don't want to do that in production. Anywho, if we get rid of these again, this will be a follow-up video. Thanks for watching, as always. I'll stop there. No plan or purpose on this video. Thanks for watching.